One of the most important pieces of equipment in any repair shop is always going to be a bench power supply. Now it's a little less so lately because the whole bunch of laptops are powered with USB-C. The same goes to the phones. So it's not like it used to be where you just connect a USB port to the power supply, you supply 5 volts and you see how much power it grabs. And now the phones need to identify the charger to determine what current they can actually draw from the power supply. It's primarily a safety feature, for which case you can get one of these. This is the USB-C power meter and just any USB-C charger. And you have a bench power supply for phones, maybe laptops, not very powerful laptops. The more powerful laptops, again, it's not like it used to be. They do use ID pin, and that ID pin can either be the charger presence, so it just goes to ground if the charger is fully inserted. That's a little older design, especially on Acers. Dell's and Lenovo and all of those, even if the laptop is not very powerful, it requires an original charger. That additional pin actually transmits data. It tells the computer what is the maximum power that the charger can deliver. Again, primarily a safety feature. However, bench power supply can be used for a variety of other purposes. Most notably, voltage injection. If you're looking for a short on the board, it's the easiest way to go about it is to just inject some voltage and see what's heating up. Whether you're a technician and primarily repair stuff, or you're more of a tinkerer, DIYer, and you design circuits, you're gonna need variable voltages. Now, when it comes to selecting one, the primary parameters that you will use to determine whether the power supply will suffice for your needs is going to be maximum voltage and maximum current. Most commonly, it's around 30 volts at 10 amps, giving us a full 300 watts of power. Now, some might come with additional buttons for memory. Some will come with OCP function, a constant current or constant voltage. Usually it's always going to be a constant current, so the voltage will drop to maintain the current. So if you have a short, there's going to be no more than, say if you set it to 1 amp, there's going to be no more than 1 amp going into the circuit. Thus the voltage is going to drop to maintain a constant current. Other than that, what you might need is connectivity, and that's why I got this one. As you can see, it has USB NCOM or RS232. Probably this is TTL most likely. So you can connect the computer and you can present the measurements on the screen. That's why I bought this one. However, pictures and descriptions will never tell you whether the device is usable. Well, maybe it'll tell you if it's remotely usable, but until you actually receive it, until you actually start playing with it, you're going to determine whether it's something that is usable or not. This one, not so much. This isn't something that I would recommend, but we're going to take a closer look, and it still can be usable. Although if you don't need connectivity, I would definitely not go with this one. But the power supplies with USB connectivity, they're going to be more expensive. So today we're going to test it out, and we're going to open it, see what's inside, and we're going to assess whether this is even safe to be used, because based on my observations so far, I'm a little worried. So let's get to it. Hello friends, welcome back to the bench. Thank you very much for joining me. I recently purchased this so I can present the readings on the screen, just like I can with the multimeter. And as you can see, multimeter now says 2 ohms because we are connected to this array of resistors. Now this is an array of 4 ohm resistors connected in parallel. Now 4 ohm resistors connected in parallel like this, and 4 of them, that will give us the resulting resistance of 1 ohm. Why do we need 1 ohm? Because that makes the math easier. So what we're gonna do, we're gonna push current through this these 4 resistors, and since this is 1 ohm, we're gonna be measuring voltage on them. So if there is 1 volt on these, that means we are pushing 1 amp of current through them. Or, based on the Ohm's law, if there is 1 volt on 1 ohm, that the current flowing through it is 1 amp. That's how many devices calculate how much current is going into the circuit. A lot of ICs will have that big resistor, current sensing resistor. However, it's going to have a milliohms or even microohms, so it doesn't so it doesn't dissipate too much power on itself. Because if we push 1 amp through 1 ohm, that's going to give us 2 watts, right? No, that's going to be 1 watt, sorry, I messed up my math. So we have 1 volt times 1 amp, that's 1 watt. So with 1 ohm, that's going to make calculations very easy. However, let's confirm. So if we use a milliohm meter, we have 980, 990, right? Pretty much almost exactly 1 ohm. But when we connect a multimeter, the one that you can read right now, it says 2 ohms. So we're losing 1 ohm on the wires. So that's going to affect our measurements, unfortunately. I don't have anything better than this. I could probably figure something out, but it's not that important. We just want to confirm that the power supply can operate under load, and we're going to have rough measurements of actual current going through the resistors. So first, let's take a look what we have over here. Okay, as we turn it on, we see that it is on. It is actually off and looks like it is set to 5 volts at 5 amps. We have 4 memory slots where we can store. We can see that memory 2 slot has 25 volts at 8 amps, memory 3, 10 volts at 4 amps, and 5 volts at 2 amps in M4. Now, you might find this very useful if you do the typical stuff, like you need constantly need to switch between 5 volts and 2 amps, like typical charger would have, the phone charger, or between say 19 or 19.5 and 5 amps, perhaps for a little older laptops, maybe 12 volts for charging a battery or what have you. We also have one output over here, which is 5 volts 2 amps, typical USB type A. However, this will probably not charge your iPhone, because most likely there is nothing on the data pins. Nowadays phones also need to read what the charger actually is. So again, not just 5 volts delivered to 2 pins and the phone is going to start charging. The phone would like to know what kind of charger it is using to know how much power it can drain from the device, from the power supply. Now let's see, we also have a lock. I'm not sure what that is for, probably so we can't change anything. Yeah, so no buttons work. Yeah, so that completely locks the device. I'm not sure what exactly is the purpose of this. So let's go to memory 1, and if we click adjustment, right, we can adjust voltage like so. Now if we click, we can change the decimals, right? 4, 5, then again click VA and we have 5 amps. Oh, and it disappeared. I waited too long. So let's try this again. Let's switch to 4 or maybe 7. All right, let's do 705. Then let's change, too late, I missed it. So this is number one problem with this device. Whoever, well, we'll get to that, because there was no QA, no meaningful QA on this device. This device, in my view, should never leave the concept phase as it stands right now. So now let's see if we do it a lot quicker, because we have to hustle. It switched to 6 by itself. We'll get to that. Now, as you can see, we'll get to that. But for now, let's do 7, okay, and I want to store it in number 1, but it just switched to number 1. So how do you store these? You store them by being very quick over here and there. It is stored in M2. No, it isn't. Again, let's do this, 2 amps, and yeah, that did it, right? Yeah, that did it. So again, let's switch it. You have to be very fast with this, but you can't be because the encoder is absolute crap. Let's do 5 amps and store in M2. Yep. Okay. So that's how it works. But you have a very tiny window where you can actually set that. It is very frustrating to work with this. That's why those memory buttons seem to be kind of crucial for this device to even work, to be usable. So let's start with 5 volts at 5 amps. It will, the power supply will come with these little alligator clips or crocodile clips, whichever one you prefer. So I assume we connect black here and red here. This is likely the grounding of the device, so the shielding basically. Then what we're going to do, we're going to connect our resistors. We're going to switch to voltage. Then let's connect polarity. Doesn't really matter here, but just let's keep reds and blacks together. And so we can see the positive voltage instead of negative voltage, but it really, in case of resistors, it really doesn't matter. And now to turn it on, we just press output. And we have 4.5 volts coming on the resistors, 4.6, and our current is 4.6. So it checks out. 23 watts going into the resistors. Resistors are warming up as expected. They don't seem to be warming up evenly, but that doesn't really matter. We're not testing resistors here. Okay, so now, since we have 1 ohm on the output, let's switch to 10 volts so we can push whole 10 amps on. Oh, come on. This is really frustrating, trying to set this device. So, because you have to be so quick. 10, and look at that. So this is another thing. When they show it to you on the commercial, they switch like this, right? Click and click and click and click, right? But if you do this, you're at 0. I just turned it lightly. 1, 2, 4, 6, 8, 9, and it'll jump all over the place. It's very difficult to, because no one is using these in this manner by just turning 1. Now I turned to the right and it went from 6 to 4. And we're done. We took too long. So again, 10 volts. I want 10 amps maximum. There. 10 volts, 10 amps. It's not stored in any memory, but if we click one of the memory buttons now, we lose this setting. It'll be loaded from the memory instead of stored in the memory. So this is our maximum. We should be able to push 10 amps now. So we should see 10 volts on our resistors. And turn on. And we have 9.2. And on our resistors, we have nothing. Did I disconnect? Oh, it's over. Okay, it's OL. Because I'm set to the range of 5 volts. Let's switch the range to 50 volts. And let's do output. And we have 9.17. the power supply says 9.2. So now to actually push it to its limits, because we're using wires, we're using poor connections, so the resistors are really hot. So there is a little voltage drop everywhere. So at 10 volts on 1 amp, it should give us 10 amps. At 10 volts on 1 ohm should give us 10 amps. But there's some drop here and there. So to counter that, let's switch our voltage to 11 volts at 10 amps. And let's check it now. And we have nice 10 amps, right? We're pushing 100 watts. So this definitely boils my resistors. Now to counter that, I'm going to submerge them in water to dissipate that energy quickly. And we're going to push it to the absolute limit, which is 300 watts. Okay, my resistors are submerged in a little bit of water. Now make sure you don't use salty water for this. And actually the better option would be some kind of oil. But in general, don't try this at home unless you really know what you're doing. So now what we're gonna do is set everything to the maximum. So 30 volts, 31, and 10 amps. So that should give us, theoretically, 310 watts. Let's see, the resistors cooled down significantly. So once we turn it on, it's only going to be viable for literally a couple seconds. So we're going to have to be quick because those resistors will not survive longer than few seconds of such power. So now 3, 2, 1, go, and we have 107 and turn off. Okay, the resistors survived. The water did its trick. So looks like it did pull what we expected. And now let's check. I didn't check the voltage, so let's check again. 9.8 volts. So that's 0.2 or 0.15 volts. That's probably our voltage drop on the cables. So that's why there's a little discrepancy between this reading and this reading. So we're just going to ignore that. I don't have sufficient equipment to actually test the accuracy of this. Accuracy is important for sure, but there's a lot of factors that go into the accuracy of the power supply. I'll show you something in a second. Okay, now I know there's a fan in the back of the device, which at the moment is not turning. So I'm pretty sure I know what is the how this device is actually built, but we'll test that. We'll open it and see what's inside. But now let's see if I turn it on for a few seconds. We'll see how long until the fan in the back is going to start spinning. Hopefully my water is not going to boil off too quickly. I'm putting more water on the top of the resistors. It evaporates very quickly because we're pushing 100 watts. Now the water is starting to boil. I don't know if you can hear that. That is boiling water. And the fan is still not turning on, but we're pushing stable 108 watts. Well, by stable, well, it was fluctuating a little bit for a second, but seems to be alright. 100 watts is not a lot of power, but for this setup, it's significant. Okay, you can probably see the water evaporating now from my dish. The fan is still not turning on. It's been quite a few seconds now. Okay, let's turn it off and let's let the resistors cool down a bit. As you can see, the water is boiling off. Okay, the power supply survived. The fan in the back did not turn on. All right, it does work. All right, so now a few fun facts about your cabling and measuring voltage or selecting the voltage to be applied to the device. So as you can see, that's what I use, right? I have a universal plug over here, and I have a whole bunch of different plugs that I plug in here. Like this is for, I think, Acer, and for all kinds of computers. As I said, nowadays it's not that easy to just supply power and the battery is not charging. But there's nothing wrong with the computer. It just couldn't connect to the charger, and it doesn't know what kind of charger has been connected. Thus, it will not start charging. But if you require exactly 19.5 volts, right, there's a circuitry in the laptop that will detect that, and it's got to be exactly 19.5. If it's 19.45, it's too low. If it's 19.55, it's too high. It needs to be exactly that. There's some wiggle room, obviously, but not much. So now you have to consider how long your cable is, what's the gauge on the wire, and sometimes you have to consider cleanliness of the plugs themselves. So I know that on this wire I have a drop of 15 millivolts. So if I need exactly 19.5, then I put 19.65, because at this point I will have 19.5. But the meter or the power supply on that side is reading 19.65. Very important to remember. At some point I spent a lot of time trying to diagnose the BQ chip architecture on one laptop that wouldn't, for some reason, it wouldn't get the power OK pin, wouldn't go up. Despite no shorts, I couldn't find anything on the board. And finally, I figured out that, yeah, my meter, my power supply is showing 19.5, but I had 19.35 on this side, actually where I was measuring on the laptop. So naturally, BQ chip said that the voltage is, the input voltage is too low. Maybe not necessarily a BQ chip says detects that, but something in the computer, something on the laptop is going to detect voltage being either too low or too high. Now, voltage too low or too high could indicate faulty power supply. That's why the computer won't turn on that power supply, because it fears that once it starts grabbing a lot of current, the voltage could start fluctuating a lot because there is a problem with stabilizing voltage. That's why the voltage needs to be rather exact. It all depends on the particular laptop, particular model, but that's a good rule to be aware of, that you need exact voltage, and the cables will always cause some voltage drop. So you want the cables relatively thick, preferably even shielded, and not too long. This one's actually a little bit too long. It kind of depends how much room you have, how far away your power supply is, but the best configuration is when your power supply is pretty close to the device you're working on, and all the cables you're using are relatively short, so maybe this length or this length. All the connections need to be soldered on. Don't use any crimping, don't use any twisting or anything like that. Always solder them on, because that will give you a stable connection. That's what you want. If your cable constantly suffers from a poor connection, you're gonna start falling into a very difficult repairs. Not because the repair is difficult, but because your equipment is unreliable and it causes the device to behave in the way that you interpret as there's something wrong with the device, but all it is just faulty power delivery. Now, as you can see, this is the power supply that I use, and I've been using it for maybe a couple years now, maybe a little less than a couple years. It's an excellent device. This is OneTech. I think it's Australian made. I definitely got it from Australia, so maybe I'm not sure where it's made. I kind of vaguely remember that it's Australian. It's very reliable. One thing that you can see over here, we have OCP. I'm going to disconnect the USB batteries that I'm charging right now, and I'm going to take these two wires and I'm going to short them. And as you can see, OCP detected short on the output. Now, that means OCP basically means that if we exceed 4.180 amps, the power supply will turn off. However, if we now look at the speed of this, right? Always going by 1, right? No matter how fast I go, it always goes in the right direction and always by 1. This is not what we see on the other one, right? So this is basically, this fact alone makes that power supply barely usable, and we're gonna get to that in a second. But if we drop our voltage, our current to 0.5 amp, right, and we turn it on with OCP, right? But if we disable OCP and turn it on again, so perhaps we're injecting voltage, we're going to drop to 0.09.1 volt to maintain 500 milliamps of current draw. OCP function is very important in my view. This one does not come with that function, which is really unfortunate, because it's not that difficult function, that difficult feature to implement on a power supply. However, the main issue that I have with this one, and as you can see, I haven't even tested it yet, whether it connects to the computer and it actually, what's the refresh rate, how do you even use it? Is it an open protocol like Visa or something like that? Or is it, or I have to reverse engineer it? In either case, it's not a problem. But with this encoder all over the place, and how you set the, voltages and amperage, and you just have to be really quick, it's really frustrating. This, as far as the user experience, this should have never left a concept stage. If they build one prototype of this and someone tested it and didn't see a problem with this interface and this faulty encoder, I don't know what to tell you. You probably should be doing something else in life, not this. I would love to use it, but no, I can't. And take a look how long it stays on after you turn it off. Okay, let's see what's inside. Okay, it looks like it's not actually built the way I expected it. So I expected that this will be an SG architecture, the SG chip. They're very popular for these solutions, but we have LT494. I think that's the heart of the power supply. Now we have LM358S, that's most likely an operational amplifier for some purposes over here. Now as far as production quality, I've seen a lot worse. Some components are not aligned, some soldering doesn't look perfect but looks good enough. This is most likely a standby power. The way, this actually, now it's connected to the main transformer. So, hang on. No, the main transformer would be this one, right? And this one would be standby. So, this is, so you can see that we have, let me get something to point with. We have 4 of these pins tied together and connected to the transformer directly. So this is self-contained power supply. It's very common, and one of the legs decides what the voltage, output voltage, should be. There's a little feedback coming from the other winding of the transformer, and this connects directly. So the power that it takes is directly from the bridge rectifier, so directly from the input voltage. So right after we rectify it and smooth it, it goes directly to this guy, and this guy controls this transformer, which generates our standby. So most likely, maybe 5 volts, maybe 3.3, depending on what we need. That in turn will supply the heart. Most likely this is it. That in turn will control this transformer that actually produces power. But one thing that I do not, oh no, hang on, the main transformer is this one. The big one, the big boy. But what I do not see are the transistors. Oh, there you go. Okay, because they're on the other side over here. We have 3 big transistors, so this is most likely a diode, 2 diodes over here, most likely. And these transistors are actually controlling the main transformer. So this transformer is just insulation transformer. So our chip connects through most likely these 4, so it's a full H configuration, and it controls this transformer, which in turn is connected to the transistors that control this big transformer, right? So very standard configuration, nothing really interesting. So this is our insulation, this is our standby. We have optocoupler over here for feedback, and our main chip that controls everything. Now this operational amplifier, so most likely the purpose of it is to allow the power supply to change voltages, react to current flow, right? Because we are, and this is bench power supply, right? On the regular power supply that is fixed to be, say, 12 volts or whatever, we wouldn't have this whole circuitry over here. And obviously we have our digital circuitry over here, also a whole bunch of operational amplifiers most likely, and there's going to be a microcontroller most likely somewhere that is controlling. There it is, STI, is it here? That is STM32F103R. So this is the actual heart of our device. As far as the control circuit goes, we see some very questionable soldering over here. Very questionable. And I'm not sure what that is and why it is so, but it's crap. This should not leave QA. It's some old flux, I guess, but this doesn't look like RMA flux. It could be acid flux. So if it is, then it's just going to keep corroding. I don't think you're supposed to leave this flux because it doesn't look like NC, at least not to me. And probably all you have to do is just spray it with some alcohol and brush it with the toothbrush, and that's all you had to do. But no, we didn't even do that. So as far as the build goes, it's pretty much what we expected. Looking at it now without the microscope, I see that I missed some things over here, and it's a little more complex than what I relayed, but the idea is the same indeed. It's not too bad. I don't see any particular red flags over here, maybe except that that flux not being clean, but that's not a huge deal as long as the flux is not aggressive or corrosive. I can see the thermistor over there, so that's when the fan turns on, when that thermistor detects temperature higher than a set temperature. The smoothing cups, I think, are 85C, which technically is okay. I don't know why nowadays on every power supply I see 105C cups on the primary side. I always thought that 85 are okay to be used as smoothing cups on the primary side, and 105s should be used as the output caps. But Lately, I see almost every device on the primary side has 105 caps. Probably not a big issue. I would probably use the same. As far as the capacitance, they are 680 microfarads at 200 volts times 2. Yeah, which makes this power supply work only on 120, 115 volts. I would like to see a circuit that it can work on both 120 and 230. But, you know, sometimes you just have to cut some costs. Because the only difference over here, in all honesty, because this is self-regulating circuit. It really doesn't matter what power, what voltage you supply to it. As far as the power supply goes, it doesn't care, as long as it's not higher than maximum and not lower than minimum. But for that, you can't use 200 volt caps. You need to use 400 volt caps, which means they're going to be almost twice as expensive, twice as big. The footprint is going to be a lot larger. The second thing, 680, it depends on how much power you draw, but 680, that's pretty good. Typically, what I see is closer to 220, 330. It's usually the highest. So these caps are kind of overkill over here. So instead of 680, I would probably put 330, but 400 volts. That would make this device work both on 120 and 230. We have a fuse over here along with a spare fuse, looks like. Looks like there's a spare fuse as well. Let's see, what kind of fuse is it? It's a 5 amp fuse. 5 amps. Good to know. As far as the connectivity, it looks like it is indeed RS-232. We have a MAX 232A. So this chip is a charge pump that allows the RS-232 signal to actually use positive and negative voltage. So this is not TTO. So this is true RS-232. Didn't expect that, but that's pretty cool. We have, okay, CP2102. Now, I would have to check that, but I'm pretty sure this will not work on Windows 11. I'm pretty sure the 2102 is no longer supported on Windows 11. Correct me if I'm wrong in the comments. I will eventually check that, but I'm just really not pleased with the user experience of this device, so most likely I will not be using it, but we'll see. Okay, and I think this is it. It's not bad. I do not recommend it because it's so frustrating working with this interface, but this is something that can be fixed by just issuing an update to the firmware. Now, is there an ability to update firmware by connecting it to the computer? I don't think so, but who knows. The worst case scenario, you just need to replace the microcontroller or just take the microcontroller out and flash new firmware if available. But that's something that the manufacturer could do to just update firmware so it's easier to use. The buttons feel okay, not great, but okay. I could live with the buttons. The encoder, absolute crap. This is basically what I would expect when I buy encoders, those very cheap encoders for like my DIY projects. And one thing that I always struggle with is that they just don't work. I set up an interrupt for the change, and you just kind of check whether it moved to the right or to the left every time it moves, right? But then you move it quickly and it's all over the place, or you move it slowly to the right but very slowly and it moved to the left 3 times as far as the controller is aware. So this is not a problem of the actual control circuit. This is not a problem of coding. This is just plain problem of a very crappy encoder, extremely crappy, and you can kind of feel that it's cheap and crappy. And by the way, that flux left behind, that's on the encoder. So after cleaning, encoder might start working a little better, but not perfect. It's never gonna work like this one on the real industrial device, right? It's just too cheap. Now you're asking, how much is this device? It's a crazy $150 for this crap. Absolutely ridiculous. Now, why is it ridiculous? Not because of the build. Build is fine. The power parameters, the features and stuff, it's all right. But user experience, as far as operating this device, which is the most important part of this device. All day I gotta be turning this knob, and all day I gotta be pressing and changing the settings, tweak it a little, few milliamps higher, 2 volts or 20 millivolts higher or lower. All day I gotta be using this. So if this is not working correctly, it doesn't matter. All the rest just completely doesn't matter. It can be the best circuitry ever, but with this limitation, it's just not usable. And I just checked how much I paid for it, because I thought this was closer to maybe $70. I would not be crying about it if it was $70. But 150, I don't know. I think I'm gonna have to return it. I don't want to use it. I prefer to pay maybe $300, but for a good power supply with the connectivity. But I got this one just purely for the sake of connectivity, and I figured, okay, let's just use it, even if it doesn't have OCP and stuff. Power is power, right? But no, with this one, no OCP, horrible, absolutely horrible user interface. I don't understand how someone tested this and said, yeah, it works fine. And on the pictures, again, I've seen the videos of someone presenting it, and I see, and I know why, because I use it now, that they were adjusting just click, 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 slowly and steady. No, just do this and show me that it works, because this one definitely can. And all of the devices that I use with an encoder, they all work as expected. This works like something that I would have done, with my the cheapest, crappiest parts. And you're charging me $150 for this? No, this is going back to China, and it should stay in China. Not recommended, guys. Not recommended. Don't waste your money. If you need a power supply, you can get a pretty cheap ones, $30. That will give you most likely pretty much the same capabilities as this one, only a little crappier user experience, maybe a little lower accuracy, but it'll work. The ones built on SG chip, I have a video of fixing one that we did a couple years ago, maybe. At least, if you're not happy with that one, at least you spend $30 on it. $150 for this, craziness. But we're gonna end here. I'm gonna put it back together, test it again, and probably pack it up and return it with a note that try again. This is not it. Alrighty, fellas. I hope you found this useful. Thank you very much for watching. I do appreciate you, and I shall see you in the next one.